Okay, fine. Okay, so let's continue from the last time. So last time we finished what? So we defined Czech complex. And for us, the Czech complex was just for open set. We recorded all the forms, all the differential forms on this open set. And then, well, maybe the main result of the last time was that it was somewhere here. Yeah, that's so we have this. There is a morphism between chain complexes from the forms to Czech complex, and that induces an isomorphism. So actually, you can define the RAM cohomology, you can compute it, but instead you can cover your manifold by good charts, and then just consider the Czech cohomology of the complex obtained as charts by as this like Czech chains. Well, then the idea was that basically you have some kind of B complex, so just the square table like that, and then like inside everything, let's say 0 homologically, but you have something not trivial on the left. So the column, for example, for us, this column was the column of differential forms on the manifold. And so the homology of these columns, they're equal to homology of the complex, which were here defined as homology of complexes defined by diagonals like that. And then it means that if instead of like looking at the column, we consider the here row, the picture is completely symmetric, and so actually so the same homology will be the homology of this row. So that was the idea. Okay, and as far as I understand, so that's how this Czech homology were defined. But then people start to think, okay, why not to do the same just for other groups? Why should we take the forms? Okay, so that will be the topic today. But now let me first define something. So finish the previous thing. So just some remark is that there exists an explicit map. So from the Czech complex to the complex of differential forms, such that, well, so here we have also the map R, which was defined before, such that F composition R is 1 and R composition F is homotopic to the identity. So you remember, so what we did before, so we had a, for example, we have a differential form, and then basically we just restricted to the elements of covering. So that was the map R. In other direction, it looks to be more complicated. So imagine that you have certain chain in this Czech complex. So as you remember, so what is the chain there? So you just say that, well, I have some intersections of sets, that's my covering, and on every, let's say, R tuple intersection, I define certain differential form. And then, so given such a collection of forms, like let's say on the pairwise intersections, now I'm asked to produce certain form on the whole manifold. So it's not clear how to do. Actually, there is a formula, so it's called collating formula. So F is given by collating formula. So look at the book look into bot 2. Well, because the formula is quite long, and actually when you try to prove it also it's quite long proof, but it exists. So basically if you have certain alpha, you look at its differential of alpha, and then using them you produce certain explicit differential form. So that gives you certain C null U omega K. So let's say K chain in C U omega. And that gives you certain chain like that. And here it means that it basically, so you define a chain just on elements of the covering. And so this chain happened to be agree on intersections. So actually this will be the image of F will be a form. Well, there is explicit formula. So if you want, you can just look there and well, we will not discuss it. Well, and then you can prove this formula works. What else I want to tell you about that? Well, maybe that's all. Also, you can prove a unit formula. One can prove the unit formula by similar reasoning. Again, if you wish, you can read both too, but we skip this part. So, well, that's also quite a lot of computation. It's indeed interesting to look into that, but I am not able to present it in a reasonable time and way because, well, so there's just a lot of notation. So, but I recommend to read it. Recommend to read it. Okay, but so what we do, we go to the Czech cohomology for arbitrary presheaf. So now, so that's the end of the topic about Czech homology for forms, for differential forms. Now the next chapter, it's presheafs. And Czech cohomology. So first of all, what is a presheaf? A presheaf is just a generalization of forms. So if you have just open set, U, open, you can associate to it differential forms on U. But we can do it just with any abelian group. So it presheaf it when we do it, we give it just to any abelian group. So now let's define it. So what we know about forms, well, actually we can restrict a form, right? So what we do in many places. So when we consider Meyer vectors, sequence, and so on, the basic operation we did, we just restrict a form from a bigger open set to a small open set. So that will be the definition of presheaf. So a presheaf. On topological space, it's just a function that assigns to every set, to every open set, an abelian group. So that's, well, let's call it F beautiful. Just to any open set, we assign an abelian group U, well, F of U. And well, and then we also must have inclusion map. So if you have an inclusion map, well, let's denote by I, U, V. That's a map from V to U, inclusion of open maps. So it gives us a map or restriction, right? There should be some map f also I u v which is a map from the abelian group associated to u to the abelian group associated to v. Okay, so that's it. So basically, that's you have forms associated to open set, and then we have this restriction map. That's almost everything. So the only thing we should add. So okay, so first of all, we have it may be the identity map. So if this EUV equals to identity, so I just map from U to U, then there's this map between abelian groups should be also identity. And also, what should we do? So it should not depend on the chart, let's say. So it means that if we just go from, so if we have restriction 2 times, it will be the same as a composition of restrictions. So it's also very natural property. So that's transitivity. So we also require it. So that's when you have I, Q, V, and then composition with the so okay, so here we have U, here we have V, and let's say you have a W inside, right? Then it means that we should first so there is a abelian group associated to U, abelian group associated to V, and abelian group associated to W. And so we must have the composition is equal to this one. So it means that, so we first apply f of E U V, and then we apply restriction to from V to W. It should be the same as I just restricted from U to W in one step. Okay, so that's what we require. So a presheaf is such a map associating to every open set an abelian group. And so here for any open U, such that also for every inclusion of open sets, there is a corresponding map between the corresponding abelian groups. The identity goes to identity, and the composition goes to composition. Okay. And then also one can define the homomorphism of 2 presheafs. Homomorphism of 2 presheafs is just a collection of maps, right? So it means that for every U, you associated first of all f of U, but also you associated certain g of U. So if you have a map between 2 presheafs, homomorphism, it must be a map between any such open sets. Or between for any open set U, there should be a map from f of U to g of U who commutes with all this stuff. So who commutes with restriction. So it means that f U G U, and if you have a restriction to f V, and so here we have also restriction to V, should be commutative diagram. Commutative diagram. Okay, that's the homomorphism between 2 presheafs. So another way to formulate it, an equivalent way to say it, equivalent way to say it, is to say that, well, we have if we have a topological space X, one can define category. Open X, the category of open sets in X. And so you have a category, you must have objects. Well, our objects should be just open sets. And you must have like morphisms. Morphisms, just restrictions. Well, inclusions, let's say, not restrictions, but inclusions. So if you have U as a subset of V, then there is a map inclusion from U to V. Right, and then, well, if you remember, so what we require from category, so we must have the composition of morphisms. And yes, here we have it. So if you have a like small open set, a big open set, and even big open set, that indeed we have this chain of inclusions. Okay, so we have such a category, and then it means that a presheaf is a contravariant functor from open X to sets, right? Because what is contravariant? It means that it reverses the errors, the morphism. So here we have a morphism from, let's say, U to V, right? And so that gives us the morphism from f of U to f of V. So that
Maybe
means
two abelian groups, not two sets.
no. So far it's okay to sets. So I mean, just any presheaf, just when you have two sets.
Ah, okay. But on the previous slide, you said that you have an abelian group, but I suppose that you're talking about thief. Yeah.
Let's wait. Well, sure, we can have this map just to sets, but actually we need only for abelian groups. Yeah, so let's say it's just for abelian groups. So you're right, because later everything what we will do, it will be just for abelian groups. So there are presheafs for which map its contravariant functors to sets, but then you can define cohomology of such thing. Okay, good. Well, and then a morphism between presheafs, homomorphisms, a homomorphism between presheafs is a natural transformation. Right, because what is natural transformation? When you have just two functors, and then you just want to have such a commutative diagram. So you just map any fu to any g of u such that the arrows, well, the morphisms are mapped to morphisms. Okay, and so some example. An example is that well, we'll just fix a group G, fix an abelian group G. And then just send the following. So if you have an open set, just associate it with the group G itself. Okay, so connected open set goes to the group G. Okay, so f of any u is G. If u is connected, in general, just take the f of u. It will be, I think, the sum of this G over all connected components. Of u. So what we want, well, and we also need to have a morphism. So if you have V as a subset of U, So here we have G, here we have G, just say that the map is identity. Right, and so for example, if you have just two open sets inside of big open set, so here you have this U0, U1, no, V0, V1. Here you have U, then F of V0 union V1 is just G plus G. Well, and send it to F of, from F of U, right? So here it's just this. So here it's just restriction. So here you need to have a map from F of U to here, and so that's the map. You just send the G to copies of it. So for example, it sends identity to identity plus identity. So here we should take the product, right? Not the sum, but the product. So that's called a constant presheaf. Okay, what else? Well, maybe I tell you what is a sheaf, but maybe you already know what. So a sheaf is a presheaf plus gluing condition. So for example, here, so what I say for presheaf, so maybe I have two open sets. Maybe I have some like group here, some group here. Maybe they agree on intersection. But maybe, so the map for the union of open sets will be empty. But for the sheaf, it should be possible to glue different sections. So it means that if you have certain group here, and then you have some maps to the group of intersection which coincide, you should be able to glue them. It's like this continuous function. If you have continuous functions on two open sets and they agree on intersection, then you have a continuous function, the union of them. So the same is for differential forms. If you have two differential forms on like two open sets, and when you restrict them to the intersection and they agree, then there is a differential form on the union. So when such a property holds, then this presheaf is called a sheaf. But it's not necessary to consider such a property, to assume it. Okay. Another example. Let's say that we have a fiber bundle. Right, so you have a certain like manifold, and at every point you have for example, a vector space. For example, that's a tangent bundle or just any other bundle. Maybe it's not even a vector bundle, right? So here let's say it's fiber bundle. It means that you have a fiber F. Is a fiber F. It means that for every point X in M, there is a certain neighborhood of X such that pi minus 1 of U is equal to U cross F. So it's homeomorphic to U cross F. So there's just locally, it looks like a product with F. So F may be a circle, maybe R1. And then, so define the following presheaf, which is denoted by HQ. Okay, so just by definition, HQ of U will be equal to Q's cohomology of pi minus 1 of U. Okay, so then if U is contractible, then it means that Q of pi minus 1 of U will be equal to HQ of U cross F equal to HQ of F. Right, but so it means that like for example, if f is itself contractible, so for example, if f is equal to Rn, then this HQ is 0 for small u. But if you take the u, for example, the whole manifold, it may be not 0. Okay, so it means that you have such a property that you, for example, you like locally for small sets, you have this Q's cohomology just 0, maybe some other small group, but somehow when you can consider it for the whole manifold, it's something bigger. Okay, and what else?
I'm sorry. In the definition of this spreadsheet, we mean that the that we define the or spreadsheet on the open set U, like the U cohomology of the phi minus one of U. Yeah. Like when we write that HQ of U is equal to HQ of phi minus one of U, it sounds just like strange.
So here,
okay, thank you.
Oh.
No. That you linked that looks strange.
Yeah, I see. So well, I understand your question. So let's say that we have a pre-sheaf, I don't know, H beautiful. And then we define the pre-sheaf H beautiful of U as the cohomology Q of the preimage. But here it's H beautiful. So H beautiful is defined for any open set. It's from open X to abelian groups. Yeah. So that's a quite reasonable question. So indeed, that's just beautiful H of U, and that's just usual H of pi minus 1 of U. Then here, that's again just usual cohomology, and here it's usual cohomology. So this pre-sheaf is called locally constant. So this pre-sheaf is locally constant. So it means that for every x, there exists certain u such that this H beautiful of u is constant. So okay, so when you restrict this pre-sheaf on this u is a constant pre-sheaf. On u, right? So if you have just a big manifold M, you have u here, and you can restrict everything into u and consider just open subsets of u. So you can restrict your category of open sets, just consider the open subsets of u. And then you can restrict your pre-sheaf to this subcategory, right? And so if the restriction of this, if on this subcategory, the pre-sheaf is constant in the above sense. So here, this thing. So if for any point x there is such u such that the restriction of the pre-sheaf to u is constant, then the pre-sheaf is called locally constant. So this pre-sheaf of cohomology is locally constant, but it's not globally constant because, well, certainly. So if this equality is not true, so if the cohomology of preimage is not just the product, then it's not constant. Okay, but for example, if you just consider if E is just M cross F, then this pre-sheaf HQ is constant, not only locally but constant globally. Because then for every subset U, it will be true that the cohomology of pi minus 1 of U is just the, well, or not. So wait. So what I want? No, it's not globally constant. So it's only like that for contractible U. So no, it's not globally constant, even for products. So well, if M is contractible, no, even then it's not globally constant. So that's pre-shift. It's only locally constant.
May I ask a question?
Sure.
Well, if for some reason it is not a pre-shift but shift, we can say that it is a constant.
So you mean that we consider a pre-shift, we consider a shift which is locally constant? Is it true that it's so okay? So let me write here.
Globally constant.
Yes. So if you have just okay, so you have certain x, and you have a pre-shift f from open to a billion groups, and you say that it's locally constant, and f is a sheaf. So does it imply that f is globally constant? Well, it seems so, right? So
Well, what is globally constant?
well, just constant, constant in the above sense. So here there is certain constant means that there is a group G such that just f of u is a product of G over number of connected components of U. So just for any connected U, the f of U is just the same group G. So f is constant. Yeah, I think so. So how to prove it? I think you just need to prove some kind of Meyer-Vittorius theorem, right? So if you have just two open sets, and we know that the let's say that's f of u is G equals f of v equals f of u intersect v, then we need to show that f of u union v is also G. Right? How to show it? We need just to show. So just take any element of f of u union v. So from this group, there are maps to u, to maps to v. Okay, so how to draw it? So there is a group f u union v, and there are maps to f of u, f of v, and from here there are maps to f of u intersect v. All right, and now you want to say that we know that all these groups are just, let's say, G. And we want to show that this group is also G. First of all, so indeed different elements are sent to, well, yeah, I think it's like that. So just take just any element here below, then there is a element, so I don't know, like element A. Then there is an element A here and element A here. And since it's a sheaf, so we can glue any elements which agree, then there is an element A here. So we prove that that's surjective. But certainly it's also injective, right? Because, right, so if something goes to zero everywhere, then it was zero. because again, so by this gluing property, if we have just element 0 here, 0 here, 0 here, then it comes from the element 0 here. So actually, I think that's the correct way to formulate this gluing property. That's exactly using this diagram, right? So what I want to say is that if so I think, yeah, it's formulated something like that. So you have just some of the groups, right? So you have this f of u plus f of v, and so you have this map to f of u intersect v, where you send like a and b, you send it to a minus b, and you say that this diagram is exact. Here you just say it's f union v. Yeah, so I think that's the way how we say that a pre-sheaf is a sheaf. You just say that this diagram, well, this row is exact. Okay.
Maybe we also need X to be a connected space for this. So lemma or theorem.
Yeah, you're right. But yeah. So let's say that here we just added X is connected. Otherwise, it's not true. But I don't know, we can add this to definition of locally constant, right? Because locally constant means that for every point there is such a neighborhood, and just add that this constant sheaf that should be the same group G. Well, anyway, well, that's true. Okay, so anyway, so if we have a pre-sheaf, then we can define cohomology. So if you have a pre-sheaf, then we can define cohomology. Okay, how to do it? Just very similar, in this very similar way as we did it for the Czech cohomology last time. So say we have this U, it's open cover. So it's U alpha. It's open covering of X. Then define this zero cochains or zero chains, cochains on U with values in a pre-sheaf F are the following. So just take the functions which assign to every open set an element of the corresponding group. So are functions. So how to denote them? Well, just for any UA, we just have an element of f of U alpha. Okay, so for every element of the covering, for any element of the cover, we assume an element of the corresponding abelian group. So it may be different for different open sets, maybe the same, so we don't know. So these are zero chains. Then what are the k chains, one chains? So let's so here it's like C0 U F, and then C1 U F. That are all the maps which assume which assign an element of the group for any intersection. So here it's a product of F of U alpha intersection U beta for all alpha beta. Let's say that I is ordered. So here I is ordered. Right. So it means that, well, we can order the indices just to say that here we have all different pairwise intersections. Right. So it's like all functions which assign an element of f U alpha intersect U beta for each well, u alpha intersect u beta. So you may think that for each pair u alpha, for each pair alpha beta, we have such a thing. So that's just all functions. Okay, and
I'm sorry.
Yeah.
Is it right that zero cochains of u with coefficient and reciprocity is just a product of f of u alpha
Yeah.
above all alpha? Yeah.
yes, you're right. So product of
Okay.
f of u alpha. Yeah.
Okay. Thank you.
And the same for all like k chains and so on. So it's just the same definition. And then what we have? Then we have inclusions, right? So if we have intersection of two sets, u intersect, well, u alpha beta, which is u alpha intersect u beta. Well, there are two inclusions. We can include it to u alpha, or we can include it to u beta. Right, so we can, well, denote it by d0 and d1, delta 0, delta 1. And so because of that, since we have a presheaf, that gives us maps, like when you have this product of f u alpha, we have two maps to product of f of u alpha intersect u beta. Delta 0, delta 1, well, let me denote them by the same letters. So if you have inclusion of intersection into a set, then there is a corresponding map which is restriction, right? So you just restrict f u alpha to f u alpha intersect u beta, because we have such a map in the definition of presheaf. And certainly we have then three maps to the products of f u alpha, u beta, u gamma, right? Because if you have pairwise intersection, because when we have a triple intersection, there are three maps to all the pairwise intersections. Okay, and then taking the alternating sums of these maps, we can define the chain map, the differential. So let's define delta. This will be a map, let's say, from P cochains U F to C P plus 1 of U F. Okay, so how to define for the first step? Well, for the first step is simple, how to send it from C0 to C1. So C0 is just you choose functions on every U alpha, and now you want to have functions on intersections. Well, that's simple, right? So if you have just functions, let's say elements, how we denote them? Let's say f alpha, right? Then just take the difference. So here G alpha beta equals, for example, f beta minus f alpha. And so you have two sets. So here you have an element f alpha here, you have an element f beta here. Then you can both restrict them to the intersection. So maybe they all from different abelian groups, but anyway, we can just have just a map of restriction. And then in the abelian group f u alpha beta, there are two elements, and then we take the difference. So that's it. Maybe a more fancy way to write it is like that. So this delta, let's say 0, can be written as f of delta 0 minus f of delta 1. Right, so here, I take f beta minus f alpha. Right, so here it means that it's f alpha minus f beta. Right, because I have this delta 0 here, which is restriction. So I have the corresponding delta 0 here. And then I just, well, so that's called maybe f of delta 0, right? So that's better way of notation. Yeah. Yeah, right, because that's how we denote the maps associated to, well, delta 0, that's a morphism from category of open sets, and f delta 0, that's the map between abelian groups. Okay, yeah, so then it's better to write it like that. So in degree 0, that's defined like that, but in degree n, it's just the same. So you say that, well, delta pi, so here is defined as f delta 0 minus f delta 1 plus f delta 2, and so on, plus minus 1 p plus 1 f delta p plus 1. Because what we have here, so for example, all the deltas are from the as product of f of u alpha 0, alpha 1, alpha p to the product of f of u alpha 0, alpha p plus 1, right? And so that's just intersection of, well, u alpha intersect u alpha 1 intersect u alpha p. And if you have here intersection of alpha 0, wait, so something wrong with indices. So if you have, so we should start from 1. So if you have intersection of u alpha p plus 1, then there is a map delta 0, delta 1, and so on, where we just forget the corresponding, wait. So if you have delta 0, so you should have this alpha 0. That just forgets in alpha 0, okay? So just I want to say that delta 0, that's the map from inclusion of u alpha 0 and so on, u alpha p plus 1, alpha p, since we have p elements, 2 u alpha 1, u alpha p. Okay, so here we have p plus 1 elements. So here we have p elements. So that's delta 0. So delta 1 is just forgetting the first element and so on. So it means that in order to have a consistent notation, so we should say that, so if you have here u alpha beta, then delta 0 should be mapped to u beta, and this should be mapped to u alpha. So it was all correct initially. So here it's from beta to alpha. Right, because delta 0 is forgetting the first element. And here it's delta plus p plus 1. So if you want to have delta p, then you should just forget the last one. Yeah, like that. Now I think it's correct. Right, so if we have a map delta p from Cp to Cp plus 1, so here we have intersection of p plus 1 sets, so they are numbered from delta, with indices delta 0, well, 0 until p, and so we have p plus 1 maps, which are just inclusions, and, well, now we just take the difference. Okay, so that's the definition of the differential. Okay, so we had the same for the differential forms last time. Well, and similarly, we can just check that delta square is 0, just because of parity, right? Because if we first include into, if we first forget the index alpha and then forget the index beta, we have one sign, and if we first forget index beta, then forget index alpha, there will be different sign. Right, because this, when we forget like the first of them, this index shifts by 1. Okay, so it means that, well, this claim is that so this C upper star UF is a differential complex. And its cohomology are called Čech cohomology of the cover with values in F. So its cohomologies are called the Czech cohomology of X, right? Well, of the covering of the cover U with values in F. Okay, so it means that so here, well, we can do it what I want to say. Well, okay, so we defined it so far for fixed covering. Now we should say, okay, so what happens if we choose another covering? Because, for example, we could choose a cover of just one set. We can take the whole X as a cover. So we need the following formalism. So there should be a notion of refinement. Okay, so if you have a cover, so we have cover U and cover V. Okay, so cover V. It will be the cover of this V alpha, V beta. Beta is a certain subset of indices G. It's called a refinement. Is a refinement of U. Here we have U alpha, and alpha is from I. So refinement means that in every subset we have a subset of smaller thing. So it means that, well, and so here you write that U is bigger than V. So if there is a map phi, so for each index J, we give an index I, such that B beta is a subset of U phi of beta. Okay, so any element of the cover V is a subset of certain element of the cover U. And so this is given by the map phi. That's a refinement. And then, okay, so how the cohomology of cover depends, well, change when we do refinement. Well, we should find the map. So we have a map phi upper star, which goes from C star of U with coefficient in F to C star of V with coefficients in F. Okay, how to do it? So here we have a map from intersection of any sets from the cover to the abelian group. And here we should have a map from V, the intersection of coverings of V into the group. Okay, how to do it? So we have phi of, let's say, omega. So here we have omega. And we should find its value on the intersection of certain covers here, B, P. Okay, and okay, so what is the most reasonable way to do it? So we just look at the values of omega at the corresponding U, right? So here just look at U, and here you have phi of beta 0, phi of beta P. Right, so if you know what to associate to any intersection of sets in U. Now you have intersection of sets in V. Look in which U they live, and look what is assigned to this U. Right. So the picture sounds like that. So here you have, that's U, alpha, U, beta. So here you have V, I don't know, 1 and V2. And our map phi is from 1 to alpha to beta. And then if I have certain omega which associates something to U and V, to U alpha and U beta, to the intersection of U alpha, U beta, then I look at the intersection of V1 and V2 and I associate the same. Yeah. Okay, the only thing that we can do. So that's the definition. Then this phi prime is a chain map. So it should commute with differential. Okay, let's see how it commutes with differential. So we just need to show that delta phi omega. Then we computed on what? We computed on V beta 0, beta p plus 1. And we want to see how it was defined. It was defined as this sum of -1 power I phi omega defined on the restrictions, well, on the inclusions. So here we have beta 0, beta p plus 1, and here beta I is omitted. So I from 0 to p plus 1. So that's how it was defined. And then we need to show that it's just the same as phi upper star delta omega. Phi upper star delta omega of the same thing. So how it was defined. So first we should compute delta omega and then apply phi. Right, so okay, so that's just the same as delta omega applied to U phi of beta null, phi of beta beta p plus 1. Okay, but then you see, is it just the same in both things? Because here it's also sum of -1 omega U phi of beta null, phi of beta p plus 1, and phi of beta I is omitted. And the same will be we see here, right? Because when we apply phi prime, we just when we apply phi star, we just add phi to all the indices. So it's just the same. Okay, so it means that if we have a refinement, then we have a chain map. Then we need to show the following. So if we have one refinement but two different maps, so let's say that we have this U, which is given by this U alpha, we have V, which is given by this V beta, but maybe we have two different refinement maps. Let's say phi and psi, that are two different refinement maps. So here I, here J. Then phi upper star and psi upper star are homotopic. Well, here actually we just need to construct a homotopy, right? So we must construct certain map from the Q cochains of F to the Q minus 1 cochains in V, such that we have that phi upper star minus psi upper star it should be equal to delta k plus k delta. Okay, let's say that will be the exercise. Right, so but you just need to understand on the simplest example. So what happens if you have like certain small open set living both in like in u alpha and u beta, and previously you assigned to u alpha, now you assign to u beta, so you change this map phi. So what happens with all these things and how to present it in this way? Okay, so the next definition is, well, now what's the idea? We want to say that now consider all the covers of X by all these like open sets. Now define this cohomology for every cover, then uses refinement maps to take some kind of limit. But well, now we have to define what kind of limit. So to do that, there is a notion of direct system. So a direct system of groups is the following thing. That's a collection of groups. So for example, indexed by a directed set. So Gi, where I belongs to I, that's a directed set. So a directed set, well, it's a set with ordering. So it means that I is ordered. So that may be partial order. Partially ordered, such that or maybe we don't need it. Yeah, so it's a partial order such that if you have alpha less than beta inside I, then you have a map from G alpha to G beta. Well, now it's a question, so in which direction? So let's say if alpha is bigger than beta, then there is a map from G alpha to G beta. So here kind of B is smaller, it means B is a refinement of alpha. So that's the idea. Okay, so there should be some maps. This maps alpha beta, so from here. And so there should be the map F alpha alpha must be identity. And you should be able to compose it. So if you first restrict to beta and then restrict to gamma, it should be the same as you first restrict to gamma. Okay, so let's assume that we have such a system of groups. So it may be just ordered set, just like G1, G2, G3, G4, and so on. But maybe just a partial order. So it's not necessarily the complete order. Okay, so now we want to define the limit of it. So how to define the limit? The direct limit. The direct limit. So the most yeah.
I'm sorry. I suppose if we're talking about the direct system, the direct limit, but not about inverse system, inverse limit, or just projective limit, the arrows are from the less number to the bigger number, just like it's direct.
I don't know. You see, so it's always confusion. So surely, if you have any order like A bigger than B, alpha bigger than beta, so you can reverse it. You have a limit like that. So now let's see. So so it
just
depends
like
in which direction it's unordered.
but there was just like a standard definitions from the category theory.
So let's see. So well, I mean, I can write you like that. So I can write it like G minus 1, G minus 2, G minus 3, G minus 4. And so far there is no difference. I mean, I can just reverse the order. So how I define the direct limit is defined as follows. So you just take the product of all these things. Okay, so okay, not the product. You take the disjoint union of all GI, and then you define the thing as follows. So you just say the two elements are equal if they equal after some number of, no, it's in some restrictions. So A equivalent to beta if there exists certain, so this is from G alpha, that's from G beta, with alpha prime, such that if there is this certain gamma, such that F alpha gamma of A equals F alpha prime gamma of B. Okay, so if two elements become equal at some moment after I apply this thing, that they are equal, they're said to be equal. I think that's the direct limit, because inverse limit, that's indeed, so you take the, so inverse limit is when you have something like that, like G1, G2, G3, and then it grows in that direction. Oh wait, so if it's inverse limit or direct limit. But what is your definition of direct limit?
I said that in the direct system, if alpha is less or equal than beta, we have an arrow from G alpha to G beta. And then we define, like you defined above, the elements are equal if they are equal from some number. I suppose that to check what limit is direct and what limit is inverse, we can think about the p-adic numbers or some things like that.
Wait. Just wait a second. No, as far as I remember, the difference were a bit more subtle. So it should not depend only on the direction. Okay, let's try to think. Okay, so what is the, so you say that the p-adic numbers are usually called inverse limit, right?
Yes.
P-adic numbers are called the inverse limit. And so, oh, wait, so it's my iPad somehow wants to be black. So for p-adic numbers, indeed, so you have this GPN, right? And you have this no, I think it's different, right? So if you have p-adic numbers, so what you have this map from that Pn, and that's mapped to that Pn minus 1, right? And here the just multiplication by P, right?
I suppose that for p-adic numbers, the morphism is the taken reminder, no?
Taken mod P, right? So it's taken mod. Oh wait, so what is the morphism?
Taken reminder mod P, yes.
Reminder mod.
Or yeah.
Mod P n minus 1, right?
Yes, that's right.
Okay, and so that's the chain of maps like that, and then indeed that the periodic number, that's the inverse limit of it. That's how we say it. I think that's okay. So let's check what happens here. So if you yeah, that's exactly like, so it does not move. So we have this groups G alpha, G beta. So in our case, that's Gn, right? Gn minus 1. And so here the recipe that we should take the union of all these things, that Pn, and then to declare some of them equivalent. No, it's not the periodic numbers. So if we apply this definition to this system of groups, we obtain not the periodic numbers, but kind of finite periodic numbers. This is, for example, yeah, you see, so for example, in this definition, you never have an infinite periodic number, because we take the union of all the sets and then we declare some of them equivalent. I think that here we just have, let's say that kind of finite series, like sum of AI, PI.
You suppose that if we're using the equivalence from the definition of direct limit?
Yeah. So I mean, so
if
yeah,
we don't have periodic numbers, because periodic numbers aren't direct limit.
Yeah, but so that's my argument. So that means that the definition above is the definition of direct limit.
Oh, I suppose that it's because of the it's because of the definition of equivalence. Yeah. Okay, I understood here.
Okay. Well, you see, I'm not a specialist in that thing, so indeed, I remember that periodic numbers is an inverse limit of a system. But at least as I check here, so it does not coincide with what I told you. So at least in that case, it's not the inverse limit. So it's something different. So I suppose that this definition is correct. So that's the definition of direct limit. But indeed, there always confusion about this signs and errors and so on. So it's, I don't know, like the different conventions. There's no kind of one choice which everybody follows. Okay. So, okay, so here you have a direct system of groups. We have, we can define the direct limit of all the system. Okay, and now we can ask what happens if we have this covers and refinements. Okay, so in our case, if we have U and we have refinement V, that's a refinement of U, then we have a map from this cohomology with coefficients in F to the cohomology with coefficients in F, but with cover V. And so it means that this thing H, U, F indexed by U, just open cover, is a direct system of groups. So we can take the direct limit and say that it is the Czech cohomology of X with coefficients in F. That's the limit. That's direct limit of this thing. Okay. Yeah, I think the difference between direct limit and inverse limit is that for direct limit, there are maps from all these groups to the direct limit. Right, so this map from all these groups to direct limit. But for the inverse limit, that's vice versa. There's a limit from the inverse limit. There is a map to all these groups.
Yes,
Okay.
certainly.
Yeah, I think that's how you define. So it's kind of some universal object. So you have the direct system, and then you put something like where there are maps from all these groups and all this commutative, and then you take the universal object in these diagrams, and you call it like direct limit. But if you take objects with maps to all these groups, then it's the universal object in this category is called the inverse limit. Yeah, and so since this here, that's a direct limit, and here, so from any cover, if you compute the cohomology, there is a map, to this limiting cohomology. So that's called, it is called the Czech cohomology of X with values in F. Well, and then, so what actually we proved before that suppose that, well, let's claim that let's R be the constant constant presheaf on manifold M, and then the Czech cohomology, this values in R is isomorphic to the RAM cohomology of M. Okay, and well, so how to prove it? So, for example, you remember, so what we do, we reduced in our computations, we reduced the computation of cohomology of M to the fact that if you take the cohomology of, well, Rn with coefficients in differential forms, then it just zeros cohomology, which are non-zero, all the others are zeros. But the same is true when you take the constant coefficients. Okay, so it means that since we have these two presheafs, so one presheaf is just constant presheaf, and another presheaf is just presheaf with differential forms. And since for Rn, the cohomology are the same, then the cohomology are the same for any manifold by this Meyer-Vittorius argument. And so it means, so last time we checked that the Czech cohomology with coefficients in presheaf of differential forms is the same as the RAM cohomology. But now we see that if we just consider presheaf with constant values, then it will be also the same. Okay, but also it means it's enough to take just any good cover, because for all good covers it's just the same. And here, for any cover, one can find a refinement, which is good. That's some theorem about manifolds, right? So if you have manifolds, if you have just any cover, then there is a refinement of this cover such that all the intersections, all the fine intersections, they are homomorphic to Rn. That's some fact from topology of manifolds. right? So you remember how we find just how we prove that any manifold has a good cover. We just introduce certain metric on this manifold and then consider a small disk in this metric. But all the same can be done if you consider the, like if you start with the cover, right? So you initially have a cover, and then just for any point you find small disk inside this certain element, and then this cover by small disk is a good cover. Okay, so that was what I wanted to tell you about Czech homology. Well, are there any questions? So let's discuss it, because here it's mostly definitions, not any theorems.
Yeah, I have a question. And why do we care about what this Czech homology with coefficients in preshifts? In what way they are better than the usual Czech homology?
Well, I don't know. So one thing to care about them is that so there is also algebraic geometry. Well, so here it's like smooth geometry, smooth manifolds, and all the charts are the same. They're just Rn, and all the homology are like trivial. But if you consider some algebraic manifolds, then you also have charts which are given by algebraic charts, like equations, complements to some zero set of something. And then you also can define the presheaf, let's say presheaf with differential forms, but then the topology can be very different. So you can consider like singular manifolds, singular varieties, so singular algebraic varieties in algebraic geometry. But still there are always some local structure. And then also for us, for example, if you have this constant sheaf, it's just the same for all open sets. But in algebraic geometry, it may be different. Like at singularities, you have another presheaf locally. Because, well, because you want to compute cohomology for algebraic varieties too, which are not necessarily smooth. I think that was the reason why people like indeed studied presheafs very, very much. And then you can formulate the Poincaré duality also for presheafs. Why is that? Well, because in a sense, when you have maps between like varieties, so it's easy to see what happens with presheafs, but with sheaves it's not necessarily obvious, right? So as we see here, so sometimes when you define the presheaf on Y via the cohomology of its preimage, so it may be not locally constant. Imagine that you have a map which is like not everywhere defined. Maybe it has some like critical points and so on. Still, it means that you can, if you have such a map, you can define a presheaf on Y by, like, let's say, cohomology of this like P-1 of U. And then for such kind of presheafs, you can also define this Poincaré duality and other stuff. And it happens that indeed this higher, like this generalizations of dualities for presheafs are very important. For example, if you studied some algebraic geometry, this is third duality. Actually, third duality is also this kind of highly sophisticated way of saying something about Poincaré duality. So it means that you can, so if you speak only about smooth manifolds, you don't need anything like that. But if you live in the world of algebraic geometry, and well, many things that can be formulated only in terms of presheafs, which are not locally constant, which are quite weird, especially for singular manifold, for singular varieties. But we need it. Okay, is it better?
Okay, yeah, okay. And in terms of computations, is it easy to compute this cohomology, these coefficients in presheafs, like to compute the direct limit? Usually, well, like how hard it is?
Well, so next time I plan to have something about sphere bundles, and so it's actually it's not about you see how to say that. So next time there will be some examples, so that we don't want to compute the cohomology, but rather we want to compute some representative of a given class. So vice versa. We have a cohomological class. We know that, for example, it exists, it's not zero, and we ask how to compute a representative of it. So we want to choose, for example, we have a system of charts, and we want to find a very concrete differential form in every chart to represent a given cohomology class. It's not trivial at all. So actually, so it's kind of inverse problem. So some people, they want to compute homology of some manifolds, but actually there are not many manifolds. So for all reasonable manifolds, you compute the cohomology. So you know it. But then there are like other questions about like representativity of classes and so on and so on. So sometimes it's important to have like concrete representatives. And how to do it? Well, one way to do it is using indeed this Czech homology, because all this, let's say, when you have the cover, right, and then you just know how all this like forms behave, you can indeed try to construct form on every element of the cover such that they are glued together and so on and so on. Because this Czech cohomology are much more concrete. You always work with, let's say, with representative. So you always have differential forms. But sometimes these differential forms are given not on like the whole manifold, but for example, on the intersections. So it's kind of the question how to extend the differential form from intersection to the whole manifold. But when you work with usual de Rham cohomology, you always work with some equivalence classes. Just all computations. So, well, okay, so you have a equivalence class of something. How to choose a representative? Well, no way. You just know its dimension, for example. So you know that when you have a factor R2 by R1, that's one dimensional. But how to choose a representative there? But here in this like Czech approach, all these things are very concrete, but they are not globally defined. So like there's a question how to globalize something that you know locally. Well, also, for example, so here it's related to spectral sequences. So spectral sequences are useful in algebraic geometry. So when you try to compute cohomology of something. So for example, you have a map from X to Y, you know cohomology of Y, and you know something about this map, and you want to understand something about cohomology of X. Or like in homotopy theory, you use spectral sequences. But for manifolds, if you're interested only in manifolds, you don't need spectral sequences. So you see, it depends on what you want to compute.
Okay, and another question, maybe I missed it, but so the homology for the manifolds, we know that they are homotopy invariant. But in the algebraic geometry, as you said, what this Czech cohomology, they will be invariant under what maps? Like up to what equivalence they are invariant?
So it depends, because so here as you see, we define cohomology with coefficients in a given presheaf or a given sheaf. So like for manifolds, it's clear what kind of sheaf you look like. So maybe it's a constant sheaf or a sheaf of this differential forms. But in algebraic geometry, there are many sheaves. There is also sheaf of differential forms, but there are other sheaves, and you can always So for example, if you consider algebraic geometry and you look at varieties up to birational isomorphisms. So birational isomorphism, for example, it's kind of meromorphic map, right? So it's not everywhere defined, but where it's defined, let's say just 1-to-1. Then this cohomology with coefficients in differential forms, they're not invariant. So a large part of algebraic geometry is trying to find some invariants, which are kind of can be formulated differently. If you consider algebraic varieties up to, let's say, this regular morphisms, then like any cohomology defined with any shifts the invariant. And like there are no simple ways to say what is the homotopic algebraic varieties. So there are some notions which are kind of, you know, generalizations of that. So in St. Petersburg, there's Panin, who is doing that like for many years. But this like homotopical algebraic geometry, but it's also not quite about homotopies. It's just an algebraic way to say that something is homotopic, even though geometrically it may be not at all like that, but which also makes sense on refined fields and so on and so on. So like the short answer for that, well, if you have just, you know, isomorphism that everything is invariant, but homotopy equivalence is complicated things to even define. And if you look at not at biregular isomorphism, but up to like birational isomorphism, then like nothing is invariant, like nothing like simple. We need much more complicated invariants.
Okay, thank you.
And is it right for Czech homology that we have some fact similar to the fact in the end of the previous lecture, that if you have some very good cover with a trivial homology of intersections, then we have that the Czech homology of the whole manifold will be equal to the Czech homology
Yes, exactly. Yes.
Covering with the coefficients, but not with the constant coefficients and coefficients with coefficients and Prishev, yeah.
Well, I guess that's true. That so indeed you want to find some subset of covers which are good in some sense. For example, that yes, so such covers as if you take the finite intersections, then cohomology of all finite intersections are trivial with coefficients in a given Prishev. So if you look at the manifolds, then there's good covers such that all the intersections are just contractible. Well, well, in any cover, you can find a good refinement. And because of that, indeed, it's enough to take just any good cover, because for all good covers, the homology are the same. Is it true just for, but well, then if you just have some strange Prishev that, well, I don't know. So usually people try to indeed, so if you have some strange Prishev which is not locally constant, they try to do this kind of this operation, try to find some, you know, some another object which with the map there, such that the Prishev can be computed using this, you know, things like that. That's what people do. But in general, well, I don't know.
Okay, thank you.
You can ask maybe some algebraic geometers about that. And also there is a book which is called Sheaves on Manifolds. It's Kashivara Shapiro. Kashivara Shapiro. Sheaves on Manifolds. Well, and there you find all this stuff, and also well, if you just look to find something in the internet, so just try to Google the Verdier duality. Verdier, like that, duality. Verdier. Verdier. Well, I don't remember. Well, I will send to the chat later. Okay, then that's
Well, I have a remark on our discussion about a locally constant sheaf to be a constant sheaf. Well, I searched over the internet and it seems that the requirement for X to be connected is not enough, but the requirement of a simple connection is enough.
Okay.
So it is not so simple.
Yeah, well, maybe it's even simply connected, not enough. So let's think. So let's say that. So here. So let's say that. So not enough. Okay, thank you. Thank you for your remark. Good. So let's think about that. Well, then I stop the recording for today. So next time we go to sphere bundles and well, how to apply it in computations. So far it was algebra. So now we go back to forms, to differential forms, and we'll try to do all this like Chekhov homology explicitly. Okay.